it's a nice class because it gives an overall view of the course, which is good to appreciate. I mean, the appreciation becomes much better. I don't think we should wait. It's already 5 minutes. That's 2 minutes slow. Yeah, 5 minutes is done. So I'll take admins later. Further, good. There are two of you, so there might be some disturbance. So something happening. The electricity connection at home is not proper. So I arranged for things before I left. Let's see where they call me. Okay, what I thought I'll do is I'll this is what shall I say, a review of the course today. We have completed the portions for the course. I'm not going to go through every single slide, but just run through things and point out take home messages, okay, which I thought you should know at the end of the course. So that way it will be good. And also, this will give you an overall view as to how the course was organized and so on and so forth. Might have been, they were communicated earlier, but the appreciation might be better at the end of the course after you've gone through the material. So we looked at reactive species and how they are important. And the take home message here is there are positive aspects as well as negative aspects as far as our perception goes with reactive species. The negative aspects are much well known compared to the positive or the needed aspects. The bottom line is reactive species are required for homeostasis, rather, reactive species homeostasis is necessary for life to occur, life in a cell to occur. And reactive species have very many different um, relevances. They are pretty much there everywhere. They are so omnipresent that I don't even think about whether they will be relevant when I take up a problem. Okay, I'd say I'll find an angle to this. Right. So Ankita knows about it. She wanted to look at something else. I said, fine, I'll find a way. I did. I didn't have to, I didn't have to think much. I found a way to include reactive species in our work, which is different from what was mentioned earlier. And of course, this is, although this course is on biosystems, reactive species have relevance in many different systems. Okay. So this is one take-home message, which I think you are comfortable now. There is no proper definition of reactive species. Okay, they are typically reactive, but their reaction rates vary over a very wide range, 10 or 11 orders, 10 orders of magnitude at least. That is one. Hydroxyl superoxide, all these are second nature to you now after the course. They derive from oxygen, nitrogen, sulfur, halogens, and so on and so forth. And you know what a dot means, you know what a negative means now. We don't have to look at this. The history of oxygen is interesting because oxygen is the main source of our reactive species, reactive oxygen species. It's good to know that there was no oxygen when Earth began, and then the photosynthetic organisms are attributed to the rise of oxygen in the atmosphere. And however, we know that the reactive oxygen species causing nature of oxygen makes it toxic. Even 21% oxygen can be toxic and so on. Okay. It's nice to remember this, an important set of reactions in the cell. One electron reduction of, in fact, this is pretty much the only place where oxygen is directly needed in the cell apart from the side needs. Oxygen, one electron reduction gives you superoxide, dot O2 dot minus. 2 electron reduction of oxygen gives you hydrogen peroxide. 3 electron reduction gives you hydroxyl radicals. And a 4 electron reduction gives you water. So oxygen going to water pretty much is the basis for all the complex set of reactions in the oxidative phosphorylation pathway. It's nice to remember this with the electrons and the charges and so on. Electrons and the free radical indications clear here. Of course, antioxidants, which keep the reactive oxygen species levels in check. And they could be enzymatic, they could be non-enzymatic, they could be many other things. Right. Okay. This is one main message. When we measure reactive species in our systems, we are typically measuring the pseudo steady state levels. We are usually interested in processes that are much slower than the processes associated with the reactive species reactions, and therefore we consider them to be at steady state. That's it's a good assumption. It works very well for our needs. It gives an, for example, the pseudo steady state level of hydroxyl radicals or superoxide radicals is a very good indicator of the cellular status level, cellular stress levels, these stress status levels in the cell. That is one main message that I'd like you to pick up. And the other main message is that what we found in our lab, that there is no correlation between the reactive species and its own antioxidant. For example, there is no correlation between the pseudo steady state levels of superoxide dismutase and superoxide. And yeah, we haven't done the other thing, so I won't say that. And that needs to be kept in mind. If we are looking at superoxide dismutase as a putative measure for superoxide, it is not. So those were the 2 or 3 main messages from the introduction. Any questions or comments that you may have? So the introduction was designed to slowly, in a story form, get you into reactive species, appreciate the importance, and so on and so forth, and pick up the principles that are central to our discussion. In the next chapter, we looked at analysis of reactions, first through thermodynamics. Okay, I can give you the bottom line. The pillars of analysis that we fall back on for these systems is, one is thermodynamics, the other one is kinetics. The thermodynamic information is pretty much of relevance, that is pretty much available in the table of reduction potentials for reactive species reactions. And it's good to remember Leo the lion says GER. Leo stands for loss of electrons is oxidation, GER stands for gain in electrons is reduction. So this is the standard reduction potential table. Standard reduction potential in this context means the concentrations of all relevant species are 1 molar except hydrogen ion, with the pH is taken to be 7. It's not 1, then the pH will be 0, and that is physiologically irrelevant. So the physiological pH is taken as the pH of definition for these particular systems, and all these values are with respect to that. All other concentrations are taken as unit molar. And yeah, if the, of course, in the cell and in many situations, the concentrations of all species will not be 1 molar. So how do you convert from one concentration to the other? Through the Nernst equation, which is this. And the relationship between free energy change, standard free energy change, and the reduction potential change is very standard Gibbs equation. Delta G naught dash is minus NF delta E naught dash. We worked out some problems and so on and so forth. Any questions on this? So pretty much thermodynamic information, standard reduction potential table, and the manipulations associated. Nernst equation. From a kinetic point of view, we looked at reactions. We categorized reactions as initiation reactions, propagation reactions, and termination reactions, which are very relevant for free radicals because initiation, propagation, termination is mainly relevant for free radicals. So if you do that, then you could invoke again a pseudo steady state assumption there and say that the initiation rate equals the termination rate, and that makes analysis simpler. So before that, we looked at some basic definitions of rate and so on and so forth, and then came up with this framework: initiation, propagation, termination. And in this context, we saw some important reactions, reactive species related reactions in this set. So you might want to just look at it whenever, as a part of this course. Yes, definitely, you've already seen this. There's a story associated with most of it, and therefore the stories are probably more rememberable than the equations. You could remember the equations that way. We also worked out some problems. Right? What else did we do? Yeah, termination reactions, and methods for measuring the reaction rate constants. In general, stop flow is for slower reactions. The faster reactions, you need a source of high energy electrons, and the reactions with superoxide and hydroxyl can be measured by appropriately enriching the medium. Any questions on this? The third chapter was on measurement of reactive species, again from our context. Right, and also we reminded ourselves that we are indeed measuring the pseudo steady state concentrations. So the concentration gives you some information, the specific level gives you much more general information that can be used across labs, across places of use, and so on and so forth. So it is amount per unit cell mass, the specific level. The measurement methods, if we focused on cultivated cells, were essentially fluorescence, absorbance, and electrical measurements at certain times. We looked at fluorescence and absorbance measurements predominantly. We predominantly use fluorescence methods in our lab, sometimes absorbance. Electrical measurements can be used. We don't do those measurements in our lab, but they can be used through a probe. Or you could separate out the products and then measure them by the GC, HPLC, and so on and so forth. Electron paramagnetic resonance or electron spin resonance, although there is a subtle difference between the two. We didn't make a difference in this course. EPR or ESR spectroscopy is the gold standard for measuring reactive species. It can measure only free radicals. It cannot measure, rather there needs to be an unpaired electron for it to measure. Otherwise it will not work, but it is the gold standard for all the free radicals. Although the interpretations are difficult if more than one radical is present, if more than one species is present, it's still the gold standard, and therefore we looked at the principles of EPR or ESR spectroscopy. Any questions? That's pretty much the take-home message. The details are always there, right? The book will come out soon. I've sent in the edited chapters too. It's just a matter of time. Then you could go back to that book. You can always go to your textbook, which is more of a Bible. It has everything in it, which is Halliwell and Goodrich. All this is there, or almost all of this is there, except our own work. Almost all of this is there. In my book, whatever was covered in the course is there. So you could always go back and refer to that whenever there is a need. Various methods are available for measurement. There are pluses and minuses associated with every single method. So you need to be aware of the pluses and minuses and be careful as to what you're actually measuring. So, and also be very careful about DCFHDA. It is still very rampantly used, although it doesn't give you much information, much relevant information. It gives you some fluorescence, which people interpret as reactive species levels, even in Nature and Science, in papers published in Nature and Science, even today. Be a little careful. Okay, I've started telling. Earlier I couldn't do much because there were papers in Nature and Science still using it. Although there is an advisory against it in a textbook, from 2015 onwards at least. Even it was known even before. So nowadays I've started saying, please refer to this. This will not measure whatever you're looking for. I mean, I understand that it is acceptable nowadays, and therefore at least mention the downsides of using DCFHDA in your paper. And then I tell the editor, if that is done, it's okay. This part of the thing is okay. There could be other comments, but this part of the thing is okay. I've started at least doing that, because still now it is kind of, I know it is wrong, but the world accepts it. So what do I do? If I say this as a reviewer, it is not really fair, because there's so many papers there, and on that strength they have used it. You cannot reject a paper on this basis, certainly, and so on. There are these periods in every field one goes through. So that way it's okay. Okay. And then we looked at, any questions on this at all? Anything that was unclear? The fluorescence method is decent, because if you choose a good enough, specific enough dye, there are such dyes available. The dyes that we use in our lab are good enough. You need to be a little careful when one interfering thing is present, but you can, right now we have standardized those. APF, HPF. Just be careful with APF if you are using it for mammalian systems, because you have peroxynitride there, and no, more than that, hypochlorite there, which will interfere heavily. Peroxynitride interferes to a certain extent, not much, but hypochlorite interferes to a large extent. With APF, it doesn't interfere as much with HPF. So we have all those interference extents that we quantified. Arsena quantified it, so we are fine with that. So those are fine. There will be other things also, but this dye will not measure those. If you need to measure those, you use another means of measuring. No. You can measure multiple things. It's just the interpretation is different. You'll have to deconvolute the signal, and so on and so forth. That requires a lot more training in EPR spectra analysis and so on. A common person, it's a little difficult to do. That's all. You can do it. You can certainly do it. You can, to a reasonable extent, apportion which comes from where and so on and so forth. But that calls for an in-depth analysis. Not very easy to do. If it's a clean system, EPR is the choice. Very clean, it will give you whatever split signal that you're looking for, and concentration is double integration of that. What was I going to say? Either through a native signal, or you can spin trap it and measure it. So either way you get one signal. If it is one, then it's not a problem. If this probe starts interfering with many other things, or there is enough of each so that each contributes to a large extent, then there's a problem. Just by problem for simple analysis. Involved analysis we can. People, there used to be a Professor Manoharan here who was an EPR expert. They can look at it and figure out ways by which you need quantum physics expertise to be able to do that. You need to work with Hamiltonians and so on and so forth. Hamiltonian is essentially a representation of energy, and the way you look at it and the way you do it, then you can deconvolute the signal. I didn't want to do that. By that time we had found out, I was going in that direction. When I came here and there was an EPR, I did collaborate with Professor Manoharan first. It went in a different way, but if I had persisted, then I could have gotten to that stage. By that time we had found out fluorescence, much easier to use. Told just switch to this, good enough. The very early students who worked in reactive species at IIT Madras did use EPR. At IIT Bombay, it was predominantly EPR. All students who worked with me. Here, very early students, I think Aparna did EPR to a certain extent, and probably one more. Yeah, not in the department. SAFE. SAFE had a EPR machine which served us for close to 30 years. So all the plots would be on paper. So you had to process that. Things had changed. And it so happened that during my time, although I didn't have anything to do with it, during my time, a new APR was processed. So when I was leaving, the new APR came. When I finished my term, the new APR came. I oversaw the installation of it, and then I left because I was in my extension period by then. They wanted me to stay on for 4 more months because the next head was caught up with something else. So after I finished my term, 3 years, I stayed on for 4 more months. I think it happened during that. So I never used it. Good machine, but I never used it because we had got it. Any other questions? We were using spin traps, DMPO and so on and so forth. We are looking at hydroxyl radicals predominantly. So that way it was okay. So we used to go clean signal. In that, I mean, in certain situations, rather for our needs, it was fine. But if it can get messed up. You could get a complex signal and then you'll have to deconvolute. Any other questions? It's just a way of understanding it. If you need to manipulate it, you need quantum chemistry, quantum physics. Yeah, then we looked at some biomarkers also for a reactive species, but be careful with the biomarker. Make sure that it actually measures what you're supposed to measure. So those were the 3 initial chapters. The 4th chapter started looking at the role of reactive species in cell signaling, the necessary parts of having reactive species, or to appreciate that reactive species are necessary for normal life. And they can affect cell signaling through their chemical effects on iron sulfur clusters, thiol groups, and histidine groups. These were the motifs which are well known. There could be others also, but these are well known. And we saw some examples of these first in prokaryotic systems and then in eukaryotic systems. How the reactive species effects are mediated to change gene expression and so on and so forth was seen. Right? So this was SOXR, SOXS, OxyR, and other examples. Is that? Yeah, there are some systemic effects also that were studied.